Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. The pros and zeros. Now we are going to discuss the properties. The properties of the properties of region of convergence here. So on the outline that we discussed, we were trying to come up with, we have reached to the point where we are going to discuss the properties of region of convergence and see how does region of convergence behave. So according to their characteristics, depending to which value you are trying to get. Properties of regional convergence. So property number one, the region of convergence, as we have seen, it appears in a ring or in the plane centered about the origin. So you remember it appears the region of convergence that is of xz consists of a ring. Consists of a ring that is in the z plane. Centered about the origin. Centered about the origin. You remember when we are drawing this kind of circle, then we say the region of convergence has a ring that is centered, for example, for any region of radius here. Then this side, for example, if the points are existing here, holes or zeros existing, then the region of convergence is going to be this. And when it is external, then you can just shade the outer side. So it consists of a ring centered from the origin. Property number two is going to be the region of convergence doesn't contain any pores. Okay, here what does it mean? So you count from where the region, they are saying region of convergence doesn't contain any pores. So which means the other one that is that are existing, you cannot show the region of convergence just considering the pores. Instead, the region of convergence becomes the zero. I mean, becomes the entire unit circle. So in that case, whenever you see the other star sign, you cannot begin from there. Instead, it's going to be external of these poles, or just before it reaches to these poles. That's where the region of convergence is going to happen. That is property number two. It doesn't contain any poles. The poles, remember how we get them? They are the denominators of the fractional numbers of Z transform, and that's how we get them. So the property number three is going to be if x of n is finite duration or finite number, the region of convergence is going to be the entire Z plane, except when Z is zero. Remember when we calculated the previous example, I think is if I say correspond the property with this equation, you can just know how to allocate the equation. So the previous equation gives exactly the property number 3, where they said if there is a finite values where we saw, like for example, 1 z plus 5 and so on and so forth, we said, let me just go back and just show you. For example, the other equation where we got z squared plus 2z plus 5 plus 7z power negative 1 plus and then z power negative 5. This covers the entire circle and therefore corresponds to property number 3. So whenever there is a finite duration, or the duration that is known, then the z transform is the entire plane, except when z is equal to 0 or z equals negative infinity. So that was the property number 3. So we are going to talk about the property number 4. If x of n, that is property number 4. If x of n is a right-sided on the other side of the circle, or the single-sided. Remember we said a right-sided should be equal to the single-sided, where we begin from the n is equal to 0 up to n is equal to infinity. And then if x is a single-sided or right-sided sequence, and if z is equal to the real numbers, or the real numbers beginning from 0, then all infinite values of z, or for example values from z modulus of r, whereby this one can be the magnitude. Remember when we calculated, we say, for example, if this is a, we say, for example, a half, less than half. So the amplitude or the magnitude or the real values can be the region of convergence at this stage. So that means whenever you calculate at this extent of n is equal to infinity of any value, for example, up to infinity of any value, for example, a power n, then you will end up getting a region of convergence will rely on this between this 1 over a, for example. Okay, we take it as a half in this case, because remember it is 1 over a minus half. So property number 5, we are still discussing about the properties. So property number 5, it says if x of n is left-sided, this also is a single-sided, and the cycle is z modulus, or the amplitude lies in this area, then all the values exist between 0 less than or equal to that value of z, then less than the magnitude of the given sigma. So this is okay. There is no equal sign. So this one will be the region of convergence. Remember, for the right-sided, this is left-sided. This is left-sided. And you remember, it ranges from negative infinity to 0. Then the region of convergence becomes like this. So it's going to be in this way. That is a property now. So whenever you calculate and using left-sided, remember left-sided is the other side of negative infinity, then the region of convergence should lie in that. And the property number 6, if it is double-sided or bilateral, the other one is the left and right was unilateral, but this one is bilateral. So if it is if x of n is a bilateral or two-sided, then and if the cycle it lies from z equals to the magnitude at r or the radius of any size, then the region of convergence will consist of a ring. So it will appear the entire ring. So the region of convergence will consist of a ring equals to z, the same ring. The entire ring will look like this. So it will be the other way around. So it will cover the whole side, not the any limit. So it will cover the entire ring of the cycle. So if it is double-sided, and that's what it means. So the whole of this is going to be the region of convergence. So there is no portion left behind. So the entire Z plane is going to have such a region of convergence. So suppose this is the center nucleus, then the whole of this is going to be the region of convergence. Yeah. Still, we are talking about the property. For example, if there is a property number 7, we have if the z transform x of z, that is the property number 7, is a rational number, then the bounded by the poles or extends to infinity. So it is going, if it is rational, then it can extend, the poles can extend to infinity. And the property number 8, if the z transform is rational and if xn is right-sided, then the region of convergence is outside the outermost pole. This is very important to note. If the z is rational, but it is right-handed sided, it's going to be bounded outside the poles. So it is going. The system is going to be magnified, or the magnitude of the poles of xn are going to be casual, and therefore region of convergence excludes or includes z equals to infinity. So it will extend to infinity. So it will go to infinity this side. So if it is a right-sided, and you have calculated them. And so you can see the properties. There are so many properties that you need to master and understand. In case when you get results, you cannot get confused once you have all these properties. Bear in mind that these properties are going to help you for easier identification. In case when you are asked so, then you can easily reply and just give it as the feedback from any lecturer that is just examining you, or any person that is interested, or any interview any interview questions that may be asked. So here the property number 9 is talking about also a rational number, but when it is left-sided, we have seen the right-sided z is going to extend to infinity. But here, for property number 9 is going to be left-sided, and it's going to happen. The other one was outermost pole is going to exist but here it's going to be inner. So it's going to be, or suppose if you have this value, then the region of convergence is going to be in this side instead of just going outside this side. So this is innermost part of it. So given this value, so that is when it is left-sided. Remember, left-sided is coming from signal, negative infinity to 0. Then unless when z is equal at 0, then the anti-causal system can be applied. Remember when we were talking the causal system and the non-causal system in our signal systems. So a ring or a disk in the z quantity of the origin is also one of the properties. The Fourier transform of x of n, continuing, for example, explaining the properties. So the property, we said it is in a ring, but also we can say, for example, if the Fourier transform of x of n, remember it is a very big x, it converges absolutely if and only if the region of convergence includes the unit cycle. So the Fourier transform is in convergence if and only if the region of convergence includes a unit circle, includes, not excludes, a unit circle. So it converges. Elsewhere it cannot converge. So these are the one of the properties. And remember, the region of cannot include any pause. This one was discussed. The final duration, this one also was discussed. This is a summary of what we have to understand. So this is a summary, and maybe there is also a table that I will share to you in case when you need them, or you need it. But also it is included in your notes when you will be sharing these notes from me, from my email address. So this is a common table. So that was the Z transform in general, comprising of its introduction, and its region of convergence, the poles and the zeros, and their properties, and so on and forth. So we have seen even how you can calculate this information. So without wasting much of our time, maybe we can just start maybe a subtopic of this, maybe the inverse now. We have seen Z transform, but we have also how do we convert the frequency, the time, signal in a continuous time signal to their corresponding discrete time signal, that is from frequency to time domain. So it's going to be the complex values here are going to be converted to the discrete numbers or discrete time values. So in that case, I would like to introduce to you the inverse Z transform. The inverse Z transform. So of course, as you understand, it is the inverse, the other way around. So it's getting back, for example, the way how we have been doing, then we turn the other way around and just get the results as opposite values. So it's going to be our opposite. So now it's going to be inverse Z transform. So it is the other way around. So it's going to be Now remember we used to have big X of Z. Now it's going to be now discrete value, whereby we will have X of n represented here. So it's going to be small x of n, which is going to be the summation. It's going to be 1 over 2 pi j, because we have worked to turn the other way around. So this one is going to be the multiple. Well, integral, because there we were just seeing the differentiation. Now so the integral to the closed loop of big X, which was the other one which we were looking for, into Z, because it's going to be n minus 1 as an inverse, and then dz. So we are going to integrate with respect to z. So here the reason why you can see n minus 1 is it's an inverse. It's like saying 1 over z power n. So when it comes there, it will be z power n minus when it becomes inverse. So in this case, this is the general equation for inverse Z transform. And I told you the purpose of this is just to get the way the other way around from frequency domain to the discrete time signal. You can get it. So before we are looking for this, now before we are looking for x of z, but now we are looking for x of n to be turned into numbers. So this is the general form. We are going to. This is the general formula for all that we have to deal with when dealing with the inverse. So the symbol here shows denotes the integral around, the counterclockwise, clockwise, then counterclockwise. Yeah. So in the circular contour centered at the origin with the radius r. So you're going to have the counterclockwise for any value here, having radius r, then going to this side, for example, taking this side as the counterclockwise. It is not clockwise. It's going to be counterclockwise. Of course, this is imaginary presentation. This is real presentation of your values. So it's going to be counter. This zero shows that's going to rotate, integrate using from the center, the control the center of the origin with that radius. Okay, we have seen what is inverse Z transform. Now we are going to discuss about the ways how to resolve this inverse transform, or the ways how we can obtain this particular Z transform. There are three ways. One is called inspection method, and we shall discuss it into details. And also there is also partial fraction expansion. So you may be given a number, then you need to use a partial fraction expansion to get that one. And also we can use power series. As I told you, there are many ways of calculating this Z transform, but particularly for this for inverse Z transform, where we want to go back and just get these values of discrete time signals, I mean values, then we have three ways of resolving the inverse transform. So maybe I can write it there so that you can see them, and when applying this or solving using this equation, you can use this equation in three ways. That is an inverse transform. One is inspection method, another one is partial fraction expansion, and another one is using power series. So number one is going to be number one is going to be inspection method. These are the ways of how you can get inverse Z transform. We have also partial fraction method. Partial fraction method, or expansion. You can expand using the partial fraction expansion. And the third one, you are going to use power series expansion. So we are going to discuss one by one as we are close to our today's session. Okay. So we begin with inspection method. In inspection method, we use a known Z transform pairs, such as common Z transform pairs that are seen in the table itself. To get an example, for example, as I told you, if I begin with this one, if I begin with this one, then I take, for example, we use the normal Z transform pairs. For example, if you have a power n, u of n, you remember we will have 1 over 1 minus az power negative 1. And in this case, it's going to be Z is greater or equal to A modulus. So all of them are modulus. So this is what we call inspection method. So now, for example, here you will have, of course, you will have to divide Z by Z all over to get equivalent to. You can also, you remember where we used to have power n, u of n, also can be seen in that way. That is 1 over minus half of Z power negative 1. So this is also true. So this is the techniques that we are using. So suppose if you are given any number and then you want to convert it to any Z transform, for example, you can easily get any number. Suppose here you have x of z, x of z is equal to 4z squared. This is plus 2 plus z. Remember, it lies in 0 greater than that value, which is z, and greater than infinity. So it will lie in this value unless z is equal to 0. Unless z is equal to infinity. So you can determine its inverse now. So its inverse is going to be, for example, you begin by, for example, if this time it's going to be, you pull 4, then you shift, for example, it is you use shifting theorem. There is going to be n plus 2, then plus 2 impulse shifted from 0, that is n, then plus 3 impulse shifted to 1, that is n minus 1. So this is n minus 1, and this is n minus 0, and then the other one is n plus 2 on this side. So this is the way how you compute. So you are going to see inverse of these, all the brackets there. And if you want to write the function wise, you can say the function, for example, the function will look like, let me write on the top because it's x of n here. So if you can take this value to this, then it will be x of n, and the function represented by 4. You can see this is a function represented by 2. This is a function, or coefficient, then 3, then 0. It is 0 whenever n is equal to 1. That is, it's like when you bring it back, it becomes n minus 1, which is this one. And also it's going to be 0 elsewhere, but n minus 1 will appear here elsewhere, and here is going to be n is equal to 0, and there it's going to be n is equal to minus 2. That is how you can interpret this function. So and it becomes this function, and therefore you can perform the other things that we said. Step number 1, you have to divide both sides by z. That is step number 2. Step number 3, you use partial fraction, for example. Then step number 3, step number 2 is using partial fraction. Step number 3, you use partial, you multiply z both sides, and step number 4, you can obtain your inverse. So to deal with this particular number, you can perform 4 steps. Let me just write them so that you cannot lose the point. So in calculating this particular number, you see z is equal to 4, the impulse function of n plus 2, like that. Then you can use 4 steps. Step number 1 is going to be divide both sides by z. Both sides by z. And then step number 2 is going to be you perform partial fraction operations, fraction. And then step number 3, you are going to multiply. So before you divide it, but here you are going to multiply both sides, by z. The other one we are dividing, and then the step number 4, which is the last one, is going to obtain your inverse. You obtain your inverse transform, z transform. So we will just continue from here and just seeing how this obtain inverse z transform of each term. Yeah. So we shall continue from here, and next time we shall just saw how we can follow these steps and see whether it can come out. So thank you.